as Larry mentioned, my name is Doug Beyerlein. Joe Brasher was supposed to be here. He's the real brains behind the Western Washington hydrology model. I'm just the guy with the gray hair, so they send me in as a substitute when he can't make it. So I'm going to go over a brief introduction of what the Western Washington hydrology model is, and then Jade's going to get to the good stuff. So you can sleep through my part and then pay attention to Jade. Okay, that said, basically what we're looking at is how climate change affects future precipitation. So that's in terms of magnitude, duration, frequency, all that fun stuff. And so how does this impact stormwater facility sizes? And so Jade will be showing you exactly how she's modeled that and what the impacts are. You'll get all the details in just a few minutes. And the real question that everybody wants to know is how much larger are stormwater facilities going to be? You know, are they going to be a lot bigger? Or are they going to be a little bit bigger? And she'll give you that information here in just a minute. Okay, so a little bit of background. So the Western Washington hydrology model was funded by the Washington State Department of Ecology. We originally created this software package about 25 years ago and have made a number of changes and updates to it since then. Now we've basically been using, the latest version has been wwhm 2012, and this is available either from Ecology's website or you go to Clear Creek Solutions website and download the most recent version. We've now created a new version which includes what we call climate adaptive tool in it, and that's what Jade used here, and we'll be talking more about that here. But the whole idea behind WWHM is we use what we call continuous simulation hydrology to compute stormwater runoff. And we do this for multiple years typically at a 15-minute time step. So a lot of numbers. And what we do is we model the entire hydrologic cycle. So we look at, when the rain falls, what does it fall on? And then how does it then move through the environment to eventually either become runoff or evapotranspiration. The water's got to go somewhere. Now, this was all basically created using what we call HSPF, which was developed, funded by EPA back in the 1970s. So it's been around for a few years. And we've done this now for the 19 counties of Western Washington. So if you're working anywhere within these counties, you're probably using our software. And so we've been using it based on historical precipitation data to compute stormwater runoff and then sizing our stormwater facilities based on that. So typically we have rainfall data that starts around 1948, and we've updated it through about 2023 in the latest version of our software. And so we've got all that rainfall data that we run through the model and then generate runoff and then use that to size our stormwater facilities. And we do this based upon flow durations instead of flood frequency. And the idea behind this is that there's a range of flows that cause erosion in our streams. And we don't want that to increase above what we call pre-developed conditions. So the idea is that when we size our stormwater facilities, we're sizing them so that the release from these facilities mimics what the pre-development runoff was in this erosive flow range. And this is what we plot up here as a flow duration curve. So we've got a blue line and a red line. The blue line is the pre-developed condition. The red line is the flow coming out of our stormwater facility. And we're basically trying to mimic that pre-developed flow. And as long as the red line is to the left of the blue line, we're good. We're not increasing the flows, but if it's to the right, then it's increasing flows, and that is not allowed. So the model does all the hard work for you, and it tells you whether your facility fails or passes that criteria. But this is all based upon historical precipitation. And so what we're really interested in is if we're designing facilities for the future, what are we going to have in the way of future rainfall? And so that's what we're trying to do here. And so with this upgrade to our new version 2025, we're giving the user the ability to do it based upon future precipitation. And this is based upon different forecast models developed by the University of Washington Climate Impact Group. And there'll be a later presentation, panel discussion this morning where you'll have a whole group of us standing up here telling you how wonderful all that stuff is. So if you want to know more details about that, you can come back for that. But anyway, what we've done is we've incorporated that into WWHM. And so we have this, what we call extreme precipitation tool that was developed by the UW Climate Impact Group. And now we've added that ability into WWHM. So you don't have to use it, but it's available there if you're interested in using it. So what I'm going to do now is turn this over to Jay. She's going to explain how Thurston County took advantage of this new feature, and then she then used it to do an analysis of how this is going to impact the sizing of stormwater facilities in Thurston County. So at this point, it's all Jay.
Great. Thank you, Doug. So Thurston County piloted this project to incorporate the climate projections from the downscaled models into WWHM, but it has since been picked up by the Department of Ecology with plans to expand it to the rest of those Western Washington counties. And the next step is using it to inform policy decisions. So what everybody wants is to know how facility sizes will change. And of course, that answer is going to be model dependent, and there's 12 climate models plus the average max and min. Within WWHM, within the update, the climate models just boil down to a percent change that scales the precipitation data, the historic precipitation. And that percent change is different depending on what frequency for each return interval, duration, and time frame you pick. So there's a lot to test from. To get an idea of what the range of those changes for the facilities could be, I tested a variety of facilities at 2 locations in Thurston County. A low rainfall location which gets about 35 inches of rain annually, and a high rainfall location that gets about 80 inches of rain annually. I created detention ponds, infiltration ponds, and bioretention ponds at both of these locations. Within WWHM, you can size your bioretention ponds for water quantity, water quality, or both. I sized it for just water quality. For those of you unfamiliar with WWHM, so what the software looks like, you build a pre-developed and a mitigated scenario. Pre-developed is what it looks like before you build, mitigated is what it looks like after you build. And when building basins in these scenarios, you have a variety of soils that you can pick from, like A, B, C, and saturated soils, vegetation types including forest, pasture, and lawn, and slopes, flat, steep, and moderate. There's also a variety of options for impervious, where the water doesn't creep in, roads, driveways, different slopes. For the tests that I ran, I tested only C soils, which are till, and for these there was no infiltration, and then B soils, which are outwash soils, and for these I used across the board an infiltration rate of 3 inches per hour. For vegetation, I tested forest and pasture. For slope, it was flat and steep. In every test I ran, the pre-developed scenario had 10 acres of whatever soil vegetation slope, and then the mitigated had 1 acre of that same soil vegetation slope, and then 9 acres of road, flat or steep, whatever was relevant. So that's a change from 0 to 90% impervious, which is a very large change. Familiar with the software or not, the update now adds this capacity to choose from 12 climate models and average max and min. Pick a return interval in years for your storm, a duration in hours for your storm, and then a time frame. After selecting all these, you'll end up with a percent change, and that percent change is what scales the precipitation data. So for my tests, I used all 12 models, not average, max, and min, a 2-year return interval, 24-hour duration, the most contemporary time period. And I scaled only the mitigated rainfall, so for the pre-developed scenario, the rainfall that was used was historic. This resulted in 416 test runs. It has been a personal goal of mine to tell 416 people how many tests I ran, so thank you for helping my dreams come true. Okay, so now we get to the big question. How will facility sizes change? For the tests that I ran, my approximately exact number I can give you is that for every 1% increase in precipitation, there was a 1.4% increase in facility size. So the chart here is percent precipitation change on the x-axis and the percent volume change on the y-axis. Each of those dots is one of the tests, and the slope of that line is about 1.4. And we can see from this that the uncertainty is a lot higher at the higher percent changes. And this isn't totally unexpected. So within WWHM, depending on where you build in location and like relevant to the closest precipitation gauge, it might be scaling your precip already, but it never scales outside of negative to positive 20% because the folks at CCS noticed things start to get a little weird at that point. The percent change range of the models just for the two locations that I built at was between negative 45 to positive 137%. It's a little outside of our 20% range, so something to keep in mind. Looking at how the parameters compare to each other, so this is that same graph with the percent precipitation change versus percent volume change, 5 times just colored by the different parameters. And the only two where there was a noticeable difference in the slopes was for facility and soil. So in this example, for every 1% change in precipitation, detention ponds have a 2.5% change in facility size. But something to keep in mind is that sea soil and detention ponds had no infiltration, and AB soils and infiltration ponds did have an infiltration rate. So it might actually be infiltration that is what we're seeing permeating, pun intended, the data here. A question that came up during this testing is, should we be scaling the pre-developed as well? To get a first look into this, I did 80 more tests for detention pond and bioretention only in the sea soil with no infiltration. And found that across the board, there was very little change in facility size when you scale both pre-developed and the mitigated rainfall. So our slope here is really flat, and overall it was less than 0.5% change in volume compared to the historic when you scale both of them. So to summarize this talk today, WWHM is one of 2 ecology improved models to size stormwater facilities in Western Washington. In a changing climate, there's going to be changes to stormwater facility sizes. And to get the ball rolling on figuring out how much we need to change the sizes, WWHM 2025 is adding in modeled rainfall projections from University of Washington Climate Impacts Group. And as a first rule of thumb, before you do your own 416 tests, you can think about it as for every 1% increase in precipitation, about a 1.4% increase in facility size, but that is dependent on facility type or if infiltration is present. Now there's the next big question of which model to use, because the model is what determines what your percent difference, what your percent change is actually going to be. So are you going to have a 10% increase in precipitation, or are you going to have 5%, 30%, 137%? And that is not a very easy question to answer. There's this famous quote, all models are wrong, some are useful. But what we're not talking about is the fact that we are currently using the historic data, which we also know is wrong. So a historic model is already wrong, it's what we're using. Maybe we can find a more useful model. Thurston County can expect model recommendations that will probably be geographic or usage based in the coming year. And we have a panel later today where we'll be talking about some of these things. It's called Enhancing Stormwater Design, Addressing Climate Change and Future Resilience, here in about 2 hours.
The short answer is no, it does not increase the evapotranspiration. We found in doing separate modeling from what Jade did that it has very little impact because of the fact that most of our rainfall is in the winter months, November through March, and we get about 27 inches on average for 40 of our 40 inches in general, and you only get about 3 inches of potential evapotranspiration there. So even increasing it there just doesn't really change things.
My understanding is the timing of the high peaks doesn't matter so much, and you can use the time series data, but it's a little bit less useful and a lot more complicated. So this is a tool that makes it easy for you to do sort of like first approximation look.
In a perfect world, we would have done what you suggested, but to make it easy for the average user to use, we simplified it because of the fact that we're doing this for all 19 counties of Western Washington, and obviously you would have a horrendous number of different precipitation time series if you tried to implement it otherwise. So it was a simplification that we made just to make it more usable. That's a perfect question to ask King County. Jeff, Berkey, do you have any comments?
So it's kind of a dual answer. There's Guillaume here with me and myself. So the county, we used to, because that's what we had originally from Cliff Mass's group for downscale. Then since then, there's been 12 others that we absolutely don't have to, this is taken away from the whole discussion, but there's no Goldilocks right now because there's so many, like Jake's been saying, it depends on the facility, depends on, frankly, it also depends on the location and the schools. I'll stop there. I don't want to go into that.
Yeah, we'll discuss this more in the panel discussion. Also, I have the software on my laptop computer here, so if anybody wants to actually see it in actual use, you're welcome to find me afterwards. After this presentation, I'd be happy to show you exactly how it works. I should be highly visible, so trouble finding me. Any other questions?
I ran 2-year, 24-hour duration, and for bioretention, they have, like, you can size it for water quantity, water quality, or both, and I clicked just water quality. But then detention and infiltration were for water quantity. Yeah, so I built 3 facilities at both locations, and then just like went through and did different types of soil, different types of vegetation, and then each one of those tests got an answer and compared it, the model to the historic. Does that answer the question?
I think I'm curious, like, if this size increase would include considerations for like detention at the, you know, up to like the 50-year or the 100-year storm, or those have yet to be reviewed.
So I didn't look at those in particular, but if the percent change was within the range that I looked at, then I think you're gonna get the same answer. I didn't check that, but it's just like it results in a percent change that scales your precipitation data. So if your 50-year storm says, oh, it's 10% more frequent versus your 2-year storm is 10% more frequent, then it's gonna scale the precipitation data the same. Right, yeah, because I was just comparing the mitigated to the pre-developed, I decided to leave the pre-developed at 0 and the mitigated at a really high percentage so that we could really see what the difference between those were. So if your pre-developed scenario had more impervious soil, then you might notice that there wasn't quite as big of a change there. Yeah, that's a good question. So I didn't look into anything other than 2-year, 24-hour duration. But again, what you get when you choose like 2-year, 24-hour this time period, you just end up with a percent change. And so that percent change, like it doesn't care if you got to that percent change by a different route. So even if you got to that by a 15-minute duration one, you would still end up with the same result. And so this was just for the purpose of getting like the full range. So if your 15-minute storm change is within that range of percentages that I was looking at, which is like -10 to 30%, then you're still within that every 1% increase is 1.4% increase in size.
Also, I'd like to clarify that when it comes to sizing stormwater facilities, we're not sizing them based upon a single storm event. We're sizing them based upon a flow duration range, half the 2-year up to the 50-year, and that's based on runoff, not on storms. So there's a significant definition difference there.
the short of it is, we need to come up with some kind of a recommendation to specifically avoid that kind of issue, right? Is to come up with what is actually the best thing that's going to give us the most useful answer.
Yeah, those kind of questions was what led to the quest to develop the tool to help inform and color the conversation.
You can pick if you are putting it on both pre-developed and mitigated, or just mitigated, or you probably choose just pre-developed, which might be interesting. So for the 416, the like main test that I did, I scaled only the mitigated data and left the historical alone.
I want to thank Jade and Doug, and I want to thank the audience.